Alright, hi everybody. I'm going to try to explain what a Jansky is by using rain as an analogy. So I'd like you to pretend that you went outside and you were going to try to count up how much rain was falling into a bucket. So here you are, here's the rain cloud, here are all the raindrops falling down, and up here you can see that actually the raindrops come in different sizes, and that's going to be important in a little bit. And I've tried to show that here. So first you have to decide what you're actually going to measure. So you decide that it'd be hard to actually count up every little drop that fell into your bucket. And plus, once they get into your bucket here, they're all just going to mix together and you're just going to have a big blob of water in there. So you have to decide what to keep track of. And so you decide to just keep track of the volume of water. So that'll be your water collected. Another important thing you should keep track of is how long you're out there for. Because if you're out there for longer, you're going to collect more water, and if you're out there for shorter, you'll collect less. So you should keep track of the amount of time that you were out there for. And what you can do is you can just take the amount of water you collected and divide by how much time you were out there for to figure out, like for example, how many liters you collected per hour. Another thing you should keep track of is the area of the opening of your bucket, because if you used a big fat bucket with a big opening, more drops would fall into it and you'd collect more water. If you used a really small opening bucket, you wouldn't collect as much. So you should also keep track of that. And so you could keep track of how many liters you collected per hour for every square meter of opening. And then finally, if you wanted to get really fancy, pretend that there was some, fancy filter that you could place over the opening of your bucket that would allow you to somehow filter out different size raindrops. And that's where this little scale at the top is going to come in handy. So if you decided to use a filter that, allowed you to collect raindrops that were, from 1/100th of a millimeter up to, about here, then only those drops would fall into your bucket and these ones would be blocked. But if you had a filter that allowed all of these drops to fall into your bucket, then you'd obviously get more rain in your bucket. So the range that you chose with your filter to allow in would be important to keep track of. You can think of it as a window of different drop sizes, and you could just say that's the diameter of the drops. Just like you used a window of time, just like you looked at a window of area, you're also going to be looking at a window of drop sizes. And so, let's just pretend that, you had this window of drop sizes. And so you let all of these drops into your bucket, and these ones didn't make it into your bucket. They were filtered out by your filter. Okay. So here's an example. So let's say that you collected 8 liters of water in a 2-hour period. The area of your bucket was 2 square meters. And coming back up to this drop size thing, let's say you decided to look at only drops that were from 0.01 millimeters in diameter to maybe 0.11 millimeters in diameter. And so this range here would be 0.1 millimeters if I subtract these two numbers. So that's your window over which you looked in drop size. So if I divide these, 8 divided by 2 is 4, divided by 2 is 2, divided by 0.1, that ends up giving me 20 liters. And I can just put a 1 beneath that because anything divided by 1 is itself. So per 1 hour, per 1 square meter, per 1 millimeter. So this is saying that I have collected 20 liters for every hour I was collecting water, for every square meter of bucket area that I had out there, for every 1 millimeter of drop size that I looked at. Another way I could write this is 20 liters per hour, meter squared, millimeter. All right, so now let's think about how that compares to a star. So here's a star, and these are like the raindrops. They're light drops, or we call them photons, and we'll say that they're pouring down into our bucket, and we're going to collect them and try and keep track of them just like the rain. So first of all, we need to decide what we're going to keep track of again. And again, it'd be hard to count individual light drops that come into my bucket. But light drops have different properties. They have wavelength, they have a frequency, and they also carry energy. So once they get in here, also, our detector, they're not going to build up in here like water, but our detector is not going to distinguish between light drops. It's just going to count up everything that comes in. And so a good idea would just be to keep track of how much overall energy was collected by our detector. So we're going to keep track of how much energy we catch in our bucket. And we're also, again, going to keep track of how much time we collect for, because if we collect for more time, then we're going to collect more light drops and therefore more energy. We also want to keep track of the area of our opening. So the bigger and wider that this opening is, the more light we're going to collect and more energy we're going to collect. So we're going to keep track of that and divide by that again. And then this time, we can't really divide by the width of the photons like we did with the raindrops earlier. In fact, what I've drawn here is really just a little representation. This is not what photons would actually look like, but I just try to show that there are differences between the photons. And up here you can see that instead of width sizes being different, I came up with a little frequency range. So different photons have different frequencies. And so this time, we're going to pretend that, well, let's say we put a filter in front of this, and it's somehow able to filter out certain frequencies and let through the filter certain frequencies. So again, we want to know how wide that range is, because if I let in, these photons into my bucket versus letting in, all of these into my bucket, then I'm going to get a different number of photons and ultimately a different amount of energy in my bucket. So we want to know the range. So again, think of that as a window over which we're looking at the light. So we have a window of time, we have a window in terms of area, and we also have a window in terms of the frequencies of light that we're letting in. So here's an example. Let's say that we put our detector out there, we catch 10 joules of energy over a time of 4 seconds, and an area opening here of half a meter squared, and the range of frequencies that I decide to catch over ends up being 1 times 10 to the 8th hertz. There's nothing special about that, I just kind of made that up. So if I do the math here, this ends up being 5. So 10 divided by 4 is 2.5, divided by a half is 5, and that's going to be times 10 to the minus 8th joules for every 1 second, for every 1 square meter of area that I collected over, for every 1 hertz of frequency range that I looked over. Or I could write that as 5 times 10 to the minus 8th joules second meter squared hertz. But there's another unit called the Janskys, named after a guy named Janskys. And a Janskys is 1 times 10 to the minus 26th joules per second meter squared hertz. So if I want to convert my answer into Janskys, it's 1 times 10 to the minus 26 joules per second meter squared hertz for every 1 Janskys, and multiplying this through, my units will cancel out, and so I will get 5 Let's see here. Oops, sorry about that. So that's 5 times 10 to the 18th. Janskys. And so that's what a Jansky is. A Jansky is how much energy you've collected per amount of time, per area over which you collected that energy, and over a certain range of frequencies.